Welcome to breadboarding. This is a small update after the second video in the breadboard video controller series, just to provide an update on some of the fixes and things that we needed to do for this. So I'll just show you on the breadboard what the various changes and things we did. The biggest one probably was that this buffer chip here was always enabled because it had both the synchronization signals going through it, the clock signal, and also the video signals. But in fact, it turned out the monitor didn't like to have the voltage for the red, green, blue signals on all the time. So we needed to actually turn this on and off. And what we're doing is we're taking this from the display enable signal here, goes through an inverter because we actually need a negative signal here. This is display enable went positive. So it goes through the inverter, comes down here. So that basically means that this turns off the buffer when we're outside the main display area, and that seems to be enough to satisfy the display. You can see here this is where our inputs are currently just tied to +5 volts at the moment, and I'm going to show in a few minutes if we hook these up actually to some of the address lines down here. These are the character address lines and the row address lines. We can actually get some test patterns on the display. One of the test patterns I actually put as the thumbnail on the previous video, and what that just allows you to do is to do a sort of a test pattern, which is a little more interesting, just single colors. What I've also done is this is the clock signal that was wired into here. So rather than taking this output from the NAND gate, which is the clear signal, which is kind of only probably about a 1/8 duty cycle, this signal here is the same frequency but is a 50/50 duty cycle, so the CRTC seems to be a lot happier with that type of signal. We've also now actually wired the vertical sync and horizontal sync directly into the output here, so they're going through the inverters here and going straight there. If we wanted to do the positive sync as opposed to negative sync, then probably what we would do is to feed these signals through the other side here, and then we kind of invert and then re-invert it, so we kind of buffer the signal. And the final thing is I thought I would try back the original 130 ohm resistors in here, so I swapped out the 100 ohm resistors back to the 130 ohm resistors, and I'll show you the calculation for this in a minute on the spreadsheet. And this seems to come out a bit over 0.7 volts. It's probably about 7.2 volts when I measured it, but it seems to give a brighter, more distinct colors on the monitor, so I think we'll stick with that higher value. And the reason why I have a 75 ohm resistor here, when you're measuring with a voltmeter, because the input impedance on the VGA monitor is 75 ohms, if you measure the output voltage here just with the meter with very high resistance rather than across 75 ohms, then you'll normally end up with about twice the voltage you're expecting. So when you attach your meter to the top end of the 75 ohm resistor to ground, effectively means that the measurement you're making is a 75 ohm impedance. So effectively the voltage halves if you've got the right input impedance. And in fact, when you measure the voltage here with the voltmeter without the 75 ohms, it's almost twice the value across here. So it means that our output impedance is almost exactly 75 ohms, which is ideal. So this is the end state of the previous video. We've also, you see here, got the signal from the clock circuit going into the counter. I might consider replacing this with a twisted pair cable at some point in time, but I don't think it's causing any trouble at the moment. And now, having shown you the changes on the breadboard, I'll just show you the schematic changes that we've done. So we've made a few changes here where we've disconnected some of these control signals from ground and just left them floating. We've changed the resistor values down here, and we'll cover the resistors in a minute. There's the display enable changes that we covered in the review of the breadboard with the inverter here, display enable here. Our clock signal for the CRTC is now coming out of this QC here, which is the 50/50 duty cycle. And so those were the main changes that we've got. So this is a spreadsheet that came from a discussion forum on the topic of choosing the correct resistance values for a video digital analog converter. Modified it slightly, so the calculations over here have got some voltages. Now the voltage, I think, and the original was about 3.3 volts. I've updated that to 3.4. You can see that the voltage comes out at just over 0.7 volts, and that's sort of close enough. We were a little bit below before, now we may be a little bit over, but that's not too big an issue. And you've got the various resistance values here, plus an allowance for the internal resistance of the chip itself. And what this shows is the calculated impedance for this circuit is almost exactly 75 ohms. And in fact, when I tested this with the meter, static test on the meter without any of the video signals running live, when I disconnected the 75 ohm value across the meter, the value almost completely doubled. The voltage I was measuring went from somewhere 0.72 volts all the way up to about 1.44 volts, which indicates that the impedance here is almost exactly 75 ohms, which is a much better bet. So these are the values that we've been running with in the video sequences that I'm showing in this video, and I've also got the various sort of combinations of hooking up the red, green and blue signals up to different data lines so we can see a slightly more varied display. So we're just using the various memory outputs from the CRTC to toggle the various color values depending on which row and column is being addressed. So this is the brightest signal, the document camera here. So I'm just going to do is to turn all of the colors off. This is kind of a grey. This is everything off. All you can see really is a reflection from the lights I've got. That's it. Dark. And if we go to just the intensity, you can see that that is fairly dark. So we're going to do all the colours first of all with the intensity off on the camera. So obviously the colour profile of the camera isn't as good, but it's quite a dark blue signal there. And then if we've got blue and green, we've got a sort of cyan colour. Blue and red should be purple. If we do colour on the display is a little bit brighter than it shows on the camera. That is the lighter red, the lighter green. This is the lighter blue, and that's the lighter cyan, lighter purple, cyan combination. So what we're going to do now is to plug these into the memory address signal. So these will be cycling through. So what we can see here, we probably need to go low enough so that we don't end up with things spanning over multiple lines. You can see how the signals change as we go. And then we'll do the brightness. So the brightness is currently high, brightness low. And if we then hook this up to one of the other signals, here, so these are very thin horizontal stripes, and if we take if we plug that into one of these, so you can see there, that's with the intensity on one of the address lines. So you can see that there is a noticeable difference between the different signals. So that's just a simple way of testing out the different color signals there, and just plugging them into the various output lines of the CRTC allows you to get some sort of idea of how the colors are actually appearing. So I hope that gave you a little bit of a better understanding of some of the changes and things that we needed to make to get these sort of signals out. So this is one of the final signals I got from the end of the video sequence, and this is what I actually used, I think, from the thumbnail image for the previous video. This has actually come from a video capture card that's going through a VGA to HDMI converter, and then from HDMI into the computer USB socket. The only issue we've got here is that the picture is shifted over to the left slightly, so we may need to change some of the timing signals for this capture card to be able to record these images more cleanly in the future. But I think this is probably a better option than trying to point webcams and document cameras at a VGA monitor, though the VGA monitor does show that it's working, but this is probably a slightly cleaner way of doing things, certainly for recording these videos. So I hope this was of interest. I will be recording the next video where we're going to be adding the character generator RAM and the shift register for producing the raster version of the character dots, and I'll be doing this in the next day or two, so hopefully you'll get the third video in this series following shortly after this one. Thanks for watching. If you don't want to miss out on the future videos, please hit subscribe. If you found it interesting, please hit like as well. Thank you.